what we're going to do is we're going to move into a newer concept. This one is particularly called enthalpy, okay? And it's related to energy. It's not exactly energy, but it is related to energy. Now we know that delta U, or U in general, is going to be an accounting of the total amount of energy that's in the system. We've seen this equation before, okay? And we know that we have work and we have heat that are associated in the system, okay? So when I get to this, I've kind of shown already that when you have work on a system, it's doing work on the surroundings or on, excuse me, on the surroundings, or the surroundings are doing work on the system, okay? So work is a measurement of a change in pressure and volume, okay? So what's happening as far as work goes, that's got to be related to the system, okay? And the sign that's associated with this is going to be negative, okay? All right. Q, in this case, we're going to keep the same. We're going to recognize that as heat. So I'm going to recognize Q for what it is. And Q is going to be my heat of the system. And all of this is still represented a change in energy. Okay? Now, when we want to measure heat of a system, we don't like to have so many variables involved with it. If I heat up a system, okay, and I have a change in energy there, then I have a change in pressure, and I've got a change in volume, I've got a lot of relationships going on, a lot of variables to account for. So I like to keep things as simple as possible. So if I have a system where the volume is going to be pretty much the same, what that means is that my volume change in the system is going to be zero. So the way we observe this is that pressure, in this case, is directly a sort of an influence on what happens to the volume of the system. As that volume changes, it really expresses what the work is. This is why your car moves, because when you blow up gasoline, the piston is being pushed on by the expanding gas. That's a change in volume. That's work being done. In this case, if I am in a system that doesn't have an appreciable volume change, which is essentially a negligible system, what happens is something mathematically irrelevant. So what happens if there's no change? If the volume that's initial and the volume that are final is the same, final minus initial is equal to 0. So if this goes to 0, what happens to this entire term? That's right, it goes to 0 as well. So this entire term drops out. Well, what does that mean for delta U then? Well, that means that delta U in this case is going to be equal to my Q value. Okay? So these two things are going to be related. Okay, and since I've managed to get rid of this particular term, all right, and this also goes for pressure. If pressure is managed to kept constant as well, this entire term could drop down to 0 as well through an additional manipulation. I'm not going to show it to you. You can read about it in the books that are provided. But here, we've got change in energy is equal to Q. Okay? Now there's another term, and what that term is delta H. Now I'm introducing enthalpy. And what enthalpy is a representation of delta U. And again, pressure times change in volume is also represented in this particular equation. All right? So I know that if pressure is the same, or if volume is kept constant, both of these are going to fall out of the system. So that falls out. So now there's a relationship here. If I take this term, so delta H is equal to delta U, I know that delta U is equal to Q from the top here. So long as pressure and volume are kept constant, my energy, my enthalpy in this case, is going to be equal to the heat of the system. Why is this important? Okay, I've just derived something for you. Why is this important? It is important because when we measure the heat of the system, what we can measure is the direct energy change of the system. Okay? Things react, their surroundings are going to change as well. Okay? Now let's do a thought exercise. And what that thought exercise is going to be is if I have a chamber, if I have a reaction that's going on, and as the reaction occurs, what's going to happen to the internal energy or to the heat of the system? Okay? Suppose that it's exothermic. What's going to happen to my Q value there? The Q value is going to get more and more negative, right? What's going to happen to that particular energy? The reaction is on the inside. The surroundings are here in my reaction flask. The energy from that reaction is going to leak out into the surroundings of the solution. And as the molecules absorb those energies, the temperature is going to go up. But I have to be careful. What do I have to be careful of? None of this stuff is going to happen in a vacuum. If you think about it, if this is a beaker on a hot plate or just on a surface in a laboratory, okay, if there's a reaction inside, energy is going to go into the solution around, but I still have an entire room full of air around, not to mention the surface that I'm sitting on. So what happens is that I lose energy to the surroundings the longer I let this reaction go. So I want something that's going to insulate my system. Okay? As far as insulation goes, I've got one thing that's great. And that one thing that's great is that which surrounds us on the planet Earth, and that's vacuum. Why is vacuum so nice? Well, if you think about a vacuum system, the vacuum system, it's got no molecules on the inside or atoms to transfer the energy from this solution to this material on the outside and then transmit that to the external universe outside of my surrounded system. Okay? To the surroundings inside. There's no way to transmit the energy from one place to another without using light. Okay? There's some metal contact, and that's where the energy is going to leak out the most. But for the most part, this is going to be a nice insulator in my system. The drawback to this, these vacuum systems aren't very reliable, okay? Unless they're made out of metal. There's some, like we tried this one time using Campbell soup cups. And those Campbell soup cups are pretty terrible, okay? Not to badmouth the Campbell company, but those cups are good for soup, bad for science, okay? Now, these things are expensive. They're made out of metal, called bomb calorimeters. And there are ways to isolate volume and you can control pressure. You can measure energy. It's in a vacuum. It's a very nice, precise way of finding how much energy inside a system. Okay? And what that means is that this thing measures the amount of calories that are coming out. So this is a calorimeter. A bomb calorimeter is one of the best things that we can use. Okay? But bomb calorimeter is not the only thing that we can use. Because when you're at certain schools, maybe like this one, we don't have a lot of money. So what we like to do is use a pair of styrofoam cups. Okay? And the styrofoam is actually a pretty good insulator. And that's going to prevent a lot of the heat loss if we work quickly in the system. Okay? So we take this, we put a cover over our system, and then we can put a thermometer into the system as well. So there's my thermometer, and I can measure the amount of energy that's being transmitted from the system by the way things react. So my solution is going to heat up. I can actually get the temperature out from my thermometer in the flask. Okay? Okay, so now that we've got our calorimeters, we're going to use the cheap calorimeters just to show you this. If I've got the start and a finish, okay, some sort of reaction goes on in the inside of one of these flasks, or in this case our cup or styrofoam cup containers. When we have a reaction go on at those inside those particular calorimeters, what's going to happen with the energy? Okay, so suppose I add some sodium hydroxide and some HCl to the system. I know that's an exothermic process. So if my initial water temperature was 25 degrees, which is room temperature, and I measure this using my thermometer, I add my two things to it, and at the end of the reaction, I'm going to have a change in energy. Suppose it goes up to 35 degrees Celsius. How do I know what's happened as far as the energy that's inside the system? The reaction, the salt, sodium hydroxide, and the gas HCl, when I've added those two things to the system, they've reacted and they've released some energy. So the overall reaction is this. I'm going to write it out for you. NaOH solid plus say HCl, and I'm going to say that that's aqueous, so that was already in here. I just pour in some sodium hydroxide and see what happens. Okay? This goes to give sodium chloride, that's aqueous, plus more water. Okay? Where's the energy going to be in the system? The energy is down here. I'm releasing energy into the system, so that means that this is an exothermic process. And we see that because after the reaction, the temperature of the water has gone up. The water in the coffee cup is the actual surroundings. Not the lab itself, not the calorimeter, but the water itself. The calorimeter does have a part to play, and it absorbs a small amount of energy. But for the most part, the water that's being absorbed here is really what's measuring that energy change. So how do I know what the change in energy that was associated with? Remember that Q value. Q is a measurement of heat. And I'm actually giving you the tools to solve this reaction. You have, Dr. Roy? I don't remember that. Well, of course you don't remember that, because it was subtle. Do you remember specific heat by any chance? Okay. Suppose that I have a cup that's got 50 milliliters of water. And we know that close to room temperature, the density of water is about 1. So if I have 50 mils of water, that means I'm going to have about 50 grams of water. Okay? And that 50 grams of water has a specific heat that's associated with it. And remember that the specific heat of water is equal to 4.184 joules for every gram that was added per degree C. Okay. Let me double check the units really bad. No, I screwed something up. There we go. All right. So joules over grams times degree C. Okay, that's the specific heat. So if we want to find out the actual amount of energy in the system, I know that Q is going to be equal to my specific heat value, which is S. Okay, so specific heat is S. If I look at my units, to get joules, I've got to figure out the amount of grams that I've got. So grams is mass here. And I've got degree C. Well, guess what? That's temperature. All right? All of these terms are measured in this case. So my units have given me what my equation is. Q is equal to specific heat times mass times T. One thing that we sometimes use is something called heat capacity. And what heat capacity is these two terms combined. And we identify that as big C. That doesn't look like a C. It looks like a crazy T. That's a big C. And what this is heat capacity. Okay? All heat capacity is specific heat of the substance times the mass of the substance. Okay? So now that I've identified that the surroundings have absorbed a certain amount of heat, do you remember that relationship between surroundings and the system? Do you? The delta U of the surroundings is equal to the delta U of the system. And these two things, because they're analogous to enthalpy and they're also analogous to heat, I can say that the Q of the surroundings, the negative Q of the surroundings, is equal to the Q of the system. All right? So we're able to actually determine what the energy is that goes on here. And I've forgotten something. All right? Q here is equal to delta T, or it's equal to temperature here. But what we're really looking for is the delta T of the system. We're looking for the change in temperature. Okay? Because the temperature remains constant, this entire thing is 0. So this is going to be our delta T. And then guess what? That's the state function. That's the one that's going to be changing here. This is a constant, that's a value. Okay? Both of those are constants. Okay? For the materials that we're dealing with. The only state function is going to be his one, and this state function is affecting that state function, energy and temperature. Okay? So, if I made this amount of energy, how would we solve that problem? Let me set it up for you. Alright, now I've got the equation set up over here. It kind of popped into existence here. But what I've done is I've taken minus Q of the surroundings is equal to Q of the system here. Okay? Now what we've got, this is the negative that's associated with the Q of the surroundings. And then I just calculate Q using the equation that I know from over here. My S value, 4.184 joules over grams times degrees C. I multiply that by 50.0 grams. And then I get the delta T, temperature final minus temperature initial. And that's going to be equal to the Q of the system. And if we look at the Q of the system, that turns out to be negative 20920. So 20,920 joules in the system. But to account for sig figs, because we've only got 3 sig figs, I'm going to use a different term. And I'm going to represent this as minus 20.9 kilojoules. Okay? And what that does is that represents what's going on in the system. That represents the amount of energy that the surroundings has absorbed, essentially, or the amount of energy that the system has released. Because this is an exothermic system, the negative Q is releasing energy to the surroundings, which is why we see a negative value for the system Q. It's the amount of heat that's been released by the system.